Hello, my name is Przemysław Ossowski. I'm from Intel, and in this quick talk, I would like to present how we can apply new hardware feature, like for example, new ISA instruction and a compiler. And in this particular case, I would like to present how we can automatically generate indirect memory access instruction for pointer tracing pattern. All right, so at the beginning, I would like to explain what is pointer tracing. So pointer tracing is simply chain of dependent load, which are serialized on address generation and so on memory access. And for example, simple memory access pattern which implements pointer tracing, we can see here. So in order to get a value from array A, first we have to read value from array B. And this scenario is especially interesting in case systems with distributed memory model, in which, for example, if we want to access different addresses, we might go through different memory controllers. And for example, in our case, it might happen that in order to get value from array B, then we have to send a request to memory controller 0, then the request returns with the value, and next request is sent to memory controller 1 in order to get the value from array A, and the eventual value we get to the core. As an alternative approach, the hardware might implement indirect memory access instruction. In such a case, such a request is sent to memory controller 0 in order to get value B, and then it is redirected to memory controller 1 in order to get a value from array A, and it eventually comes back to the core. All right, so we have new instruction, and how we can apply it in a compiler. So for such a snippet of the code, we normally generate two load instructions, and we want to replace it with one load indirect instruction, which you can see here. And this instruction is quite complex, so it will eventually end up with quite complex built-in, which has several parameters, and a programmer has exactly know which parameter means what. Yes, and it will, as we can see, it will require significant modification of the code. Additionally, if we are using built-in, then it will end up probably internally with intrinsic, which eventually, using intrinsic, will eventually lacks a common optimization on long and stored instructions. All right, so the different approach. So obviously automatic pattern detection during instruction selection on that. So thanks to do it during that instruction selection, we are already after all common optimization on loads and stored instructions. And yeah, and we are looking for such a pattern, as you can see, when there is a chain of load. One important thing which we have to take into consideration in this case is that the result returned by first load has to be eventually used only by the following load. Otherwise, implementation of load indirect doesn't make sense, and emitting of load indirect doesn't make sense, because we have to execute first load either way. All right, so we eventually end up with such a load indirect instruction, and we might say we are done, but not always. Sometimes there might be other constraints. And in our case, we were implementing, we were working on such a prototype platform which implements this direct memory access instruction, but this instruction doesn't support cached data. So it works is limited only to uncached data. But additionally, this platform has such a feature that user can configure if given access to memory goes through the cache or couldn't go through the cache. And user has such a knowledge implementing the function or a code, but compiler, based on this API, wasn't able to detect such a scenario. So how we have to tell the compiler if we can apply this pattern? Okay, the easiest way is introduction of new flag, which will tell the compiler that a given model for a given model we can apply the pattern. But it might happen that in one model or even one function, we might access different data, which are accessed through the cache or omitting the cache. So the approach which we've taken is a proposition of introduction of new pragma, which has such a benefits that it has fine granularity, requires quite small modification of the code comparing the previous one, and abstract from instruction details. So, how we handle this pragma in compiler? So, for a closing and for an opening and closing bracket of the pragma of the statement which represents the pragma, we are emitting dummy basic blocks along indirect start and along indirect end. And at the beginning execution of different passes, before all optimization passes are executed, first we go through our dedicated pass, executing dedicated pass, and all load instructions, story instructions which are between those basic blocks are marked with metadata. A load indirect, so simply available solution. And next, having such a metadata instruction decorated with metadata, during that building, we are marking those newly created memory SD nodes with new indirect allow flag. And only those memory SD nodes are taken into consideration during pattern detection, which are marked with this flag. All right, so summarizing, we have new instruction available, so we can make it available for the user through built-in function, but it's not too convenient, requires a lot of modification of the code. So automatic pattern detection is eventually what we want. But unfortunately, it's not always working. So we might provide compilation flag, but it has low flexibility regarding, and so the different approach would be pragma, which is in our case was useful and engineers could use it efficiently as they want. And at this moment, I would like to acknowledge Josh, Mariusz, Radek, and Maciek for their cooperation and suggestions. And if you are interested more, I would like to invite you for a poster session on which I will present. Thank you.